Hello my friend, in this video I will explain the logic behind this formula, this and this. Let's go. Let's say we have four objects, a triangle, a circle, a rectangle and a square. The question is, how many different ways can we rearrange them? The simplest solution is to try each way one by one. But what is the problem with it? You see, when we deal with just four objects, it's not a big deal. We can start by putting the triangle in the first position, then we rearrange the other three shapes. That gives us 6 arrangements. Now we do the same thing with the circle in front, another 6, then with the rectangle, another 6, and with the square, another 6. So we've got 24 total arrangements. Imagine there are 10 objects, or even 100, or even an object. Doing it by hand would be completely impractical. Is there a smarter approach though? As it turned out, there is a smarter approach. It is the fundamental principle of counting that I explained in my last video. We can look at the problem in a slightly different way. Instead of thinking about the shapes themselves and their positions, let's think about the slots where we can place the objects. We have 4 objects and 4 slots. Let's apply the fundamental principle of counting. Let's start with the simplest case, 1 slot. This represents the first position. If we have 4 objects to choose from and only 1 slot, then we have 4 possible choices for that first position. After choosing an object for the first slot, we move to the second slot. Now only 3 objects remain since one has already been used. For each of the 4 possible choices in the first slot, there are 3 choices for the second slot. For example, if we choose the triangle first, the next object can only be the circle, square or rectangle. The same logic applies no matter which object we choose first. So in total, we have 12 possible arrangements for the first 2 slots. Let's move faster. We already have 12 arrangements for the first 2 slots. Now 2 objects remain for the third slot. Multiply 12 by 2. We got 24 total arrangements. We apply the same logic to the last slot. We already have 24 arrangements for the first 3 positions. Only 1 object remains for the final slot. So in total, we get 24 different ways to rearrange 4 objects. I hope you got the idea. Now let's generalize it. What happens if we have n objects? At the beginning, we have n objects to choose from for the first position. After choosing 1, n minus objects remain for the second position. So for the first 2 positions, we have n multiply n minus 1 possible arrangements. Then n minus 2 objects remain for the third position because we have already used 2 objects. We continue this process until 1 object remains, and this entire product is what we call factorial. Now we understand where the factorial formula comes from. Let's move on. This time the task is different. We need to figure out how many different ways to choose 2 objects out of 4. We can apply the same principle here. For the first position, we have 4 objects. After choosing one, there are 3 objects remaining, and we are done here. There are 12 different arrangements. If you understand the fundamental principle of counting, it must be straightforward and intuitive that if we want to choose 2 objects out of n, we can choose n objects for the first position and n minus 1 for the second. I hope you got the logic. I would like to show you another way to look at this problem. You remember that there are n factorial ways to rearrange n objects. Now imagine we have 5 objects and we need to choose 2. Let's say we choose the triangle and the circle. What I want you to notice is that the first 2 objects don't change at all. The only thing that changes is the remaining objects. So intuitively, we can see that n factorial counts way more arrangements than we actually need. In a couple of seconds, I will show you how to fix it. But first, let's make a graph of rearrangements. This is for 2 objects, and this one is for 5 objects, but let's focus on a part of it. Here are some of the rearrangements that n factorial produces. Notice again that only the last 3 objects change their positions. The first 2 objects stay exactly the same. We already know that the number of ways to rearrange 3 objects is 3 factorial, which is 6. That's exactly what we see here, 6 different rearrangements, all representing the same choice because the first 2 objects never change. So, instead of counting all 6 of these rearrangements separately, we count them as just one. For every pair of chosen objects, there are 3 factorial redundant rearrangements. Let's generalize it. We have an object, and we are interested in choosing r objects out of it. We see that there are n minus r objects remaining. Taking into account that n factorial overcount n minus r factorial times for every rearrangement of r object, we intuitively understand that we need to divide it by n factorial because it overcounts by n minus r factorial times. So that's what we do, and that's what we call permutation. Another way to get this formula is also very intuitive from factorial formula itself. So n factorial is equal to n multiplied by n minus 1, then n minus 2, and so on until 1. So imagine we have n objects and we need to choose 2 objects. For the first object, we have n options. For the second object, we have n minus 1 options. So you see this remaining part. If we divide both sides by this, we get the exactly same thing. Yeah, I almost forgot. So we can rewrite this formula as multiplication of n minus I, where I is equal 0 until r. Yeah, so it actually means the same thing. So for example, let's say that we want to choose 2 objects out of n. So first is 0, so it's going to be n, multiply by n minus 1, and then n minus 2. Yeah, that's all. Let's move on. Let's say I'm going out and have to pick just 2 things out of 5. If we use the permutation formula, there is a problem. You see, permutation counts t-short and short and t-short as 2 different things. But order doesn't actually matter here. Either way, it is the exact same outfit, right? Again, order doesn't matter, and we cannot use permutation because it overcounts. The solution is simple. Just divide the permutation value by the amount it overcounts for r different objects. And boom, we get the combination formula. Everything we covered today in this video will help you in understanding the probability theory and calculus as well. So if this video was helpful, leave a like, subscribe to my YouTube channel. See you in the next one.